from scratch, right, from the very beginning, what's the first thing you need to do? Usually,
Filter.
sample it,
Filter.
filter, yes. So all these analog signals, they have an undesired DC offset. So you need to remove that first. So usually the first stage is going to be a high pass filter. So I have a capacitor at the very front stage, and you filter that out. So only leave the AC signal which carries the information, goes to the next stage, and usually it's a low pass filter, right? And then you amplify it, but at the same time you need to lift the signal to a certain DC bias in order to, because your power rails are not positive and negative voltages, not dual power supply. It's usually just a VCC and ground. So you need to lift it to the middle of the power rails, so it's able to swing and occupy the as much dynamic range as possible of the power rail, and then you digitize it. Okay, so we have to go through the whole process. And I just realized people just don't have the experience of dealing with all the signals from the very beginning. And so the general idea is to design a pulse sensor, and this will be the ASIC design. ASIC stands for application specific ICs, right? So ASIC it could be just a digital ASIC. It could be a ADC and digital and then communication protocol ASIC. So for our ASIC, it actually does pretty much everything except the amplifications, because IPGAs, they don't have analog circuits and they don't have op-amps in it, but they do have ADC. So everything after the ADC, including the ADC itself, will be on the ASIC. So in the future, it's an application specific IC. You can imagine, even though it's IPGA, but you can also tape it out through an IC chip, and that's the only chip you need to use to communicate with the OLED monitor, and eventually shows your heart rate. You can imagine the OLED LEDs are usually, it's called 1306. I don't get it. Sometimes the Wi-Fi just disconnected by itself for some reason during the lecture. For some reason, do you guys know why?
It happens in this room all the time.
Okay. So the gas is connected. Let me refresh and see. All right. So the 1306 OLED is very popular. It's low cost. So the 1306 means it's a control chip. It's a display driver chip being used for the display. So the display module integrated a lot of things. I don't know the circuit because it's packaged, so I couldn't see anything inside. But the thing is, we know it's a 1306. If you search for 1306, you can see the data sheet, you can see the timing, and they do have different versions. Some of them are I2C, and in the past we used a lot of the I2C versions communicating with Arduinos. It's really simple. Adafruit, its company developed a lot of drivers, and you can directly use their drivers communicate with the I2C port of the 1306 and eventually display something. You can directly just like a print, right? So everything is ready, programmed for you. You just directly put your characters in the print parentheses, and you directly send it to the OLED display and print it out. So that's the easy way to do it, but we are digital designers. We don't just directly just write a one line of print something as a course project. So we are designing an ASIC, right? So it's managing everything at the very bottom level. The signal definitely need to be amplified because the light penetrate your skin, the skin on the fingertip, and your blood, the oxygen in your blood can absorb the light, but the rest will go back to the sensor. So eventually, depending on how much blood you have in the fingertip, because whenever your heartbeat, when it pumps blood to your fingertip, you got more blood at the fingertip, also more oxygen over there as well. So the oxygen molecules will absorb the light, IR light. So if you have more blood at the fingertip, and you will have less reflected IR. You have one emitter, one receiver. So the emitter emits IR light, and then you get some reflected IR light getting into the receiver. If there's more oxygen at the fingertip, which means more blood, it's going to absorb more IR light and will reflect less. Okay, so you can use that very simple circuit to detect the amount of reflected light going into the receiver of the IR receiver. And that signal is a current signal. If you use a pull-up resistor, you can convert that into a voltage signal. The current will become a voltage. I'm going to draw the circuit really quickly for you guys. It's super simple. And that voltage will show a AC pattern. And that AC pattern, if you do a peak-to-peak detection, that shows your heart rate. So the thing is, for your IPGA, we usually don't do. There must be a way to do frequency measurements using just Verilog. If you're interested, you can search for that, but we are not doing it that way. So we did frequency measurement in our microcontroller class, so you can use C, right, to do the frequency measurement. The only difference is we have to use assembly to measure the frequency over here. And so you sample a certain amount of peaks or periods, and then eventually calculate the frequency, and then report it to your OLED LED display, so it knows the heart rate. Okay, so you can see that every semester I teach the embedded devices, the IPGAs. The project is a little bit different every time. So last year, what we did is we designed a PCB. Every single student designed a PCB, and they put a light sensor on it. And they didn't design it. They soldered it because they didn't have time to design the whole thing. So I designed it. I mean, just within a couple hours, and I shipped it out for fabrication. And 8 days later, I received it. The students soldered their own PCBs. So the signals were amplified, right? And they use their on-chip ADC, which is XADC, we're going to cover today, on IPGA, to digitize that signal, right? And with SPI module on the IPGA, the SPI communicates with another, with the follower, which is actually the SPI module in Arduino, on the Arduino chip. And Arduino receive it through the SPI and send it to the serial monitor through UART. So the UART serial monitor plotted the heart rate wave, the PP. I think it's called PPG or something. So it just shows the peak-to-peak voltages, and you can read the frequency out of it. So this time we are not using Arduinos. The Arduino's experiment using SPI will be just one of the labs, maybe next week. But the project wouldn't use Arduinos. There's no Arduino in the project. Let's take a look at the circuit really quick. So this is an amplifier module. So you guys are not designing the PCB, but you need to solder it when these guys arrive. So I just ordered it a few days ago. I think probably this Thursday or Friday we'll receive everything. So you can solder it. The circuit is already designed. You're not designing an amplifier and filters. This is not an analog circuits class, right? So you soldered it, and the sensor is also provided. So the sensor here has the IR receiver and IR emitter. So this is the receiver, this is the emitter. So it emits the IR light through the fingertip, and some of them will be absorbed by the oxygen of the blood, and the remaining will go to the receiver. Okay, the receiver. So in that case, it shows a output like this. Okay, so the circuit looks like this. Let's take a look at it. So that's a emitter, that's a receiver, your fingertip in the middle. Or sometimes you can even put a fingertip on the top. So for example, emitter, receiver, you put your fingertip in the middle, right? That works. But also if if you have a emitter receiver and you just put your fingertip on the top to cover both, also works. It's like shooting up and reflecting, or penetrating, and some remaining of the light goes to the receiver. Either way works. I think the sensor is probably not exactly like whatever the figure shows you. I think the sensor has emitter and receiver on the same side, so you just put a fingertip on the top. I think this is what's happening over here. So actually, is that different over here? Anyway, it's not important though. So it works, right? So it eventually shows you the output. Here, remember this is the pull up. Okay, the pull up. It's 10K. It's a pull up. So if there's no light received by the receiver, okay, so this shows a super high resistance, and so there's no current shorting to the ground. Okay, so this point as the output is being put up. It's a pull up resistor. It's being put up to VCC. The board is using 5 volts. It's gonna be a problem, right? The IPGA is 3.3 volts logic. So there are a lot of issues. I mean, that's why I like this project a lot, because it's just so practical. I have to handle a lot of things. Okay, so we'll deal with that later. I mean, the power later. So 10K resistor, put it up to VCC, and you can see here is a emitter. It's an emitter. So the BJT is just performing as a switch, right? So you give a voltage on, you turn it on, right? Turn it on, and that's the base resistor, and it's giving you a little base current, and that base current is being amplified by the collector emitter current, and you don't want this to be high, right? This is only a current limiting resistor, right? It's a current limiting resistor. It's not a pull up, so it's just like 120, 200, 300 probably are also fine, but this shouldn't be a pull up. This is a current limiting resistor. The current limiting resistor being connected into the circuit, current flows from top to bottom, and the emitter will emit our light, and it's going to be received by the receiver, and so this point will be shorted to ground and shows a low voltage, right? Depending on the amount of photons being received by the receiver, this voltage varies. Okay, so we're seeing the waves. Any questions by far? No? Okay. Do you expect a DC offset for this signal? If you enable it, is this going to be on all the time? Of course. You enable it, this is on, the switch is on, this is always on. Okay? If this is always on, is your finger, doesn't matter, you have a lot of blood in the fingertip or less blood in the fingertip, are you totally blocking the light from getting into the receiver? No. So there will be something being received. Okay? If there is something being received at a certain level, that means you are getting current to the ground, right? So this voltage wouldn't be what? Exactly. No. Wouldn't be VCC all the time, because this is not always blocked. If this is blocked, this is off, then this is put up to VCC, right? This is always VCC. However, your finger, is not totally blocking the IR light, so it's not always off here. So it's on a little bit, so you always have current flowing through it. If you have current flowing through it, it's a little amount of current, and goes through this resistor, there will be a drop, right? So this will show a voltage around, I don't know, but it shouldn't be 0, shouldn't be 5. It should be something in the middle. Okay? And then you start having more photons being received by the receiver or less, and that will be the signal swing around that static level, right? So it's going to be a AC voltage swing around a DC offset. So there will be a DC offset. It wouldn't be 0 to 5. It will be something in the middle, right, at a static level, and then the signal will swing around it. Sometimes it's lower, sometimes it's higher, but there will be a DC offset, which doesn't carry information. Maybe because it's lifting the AC signal, but anyway. So we're not looking at DC because we're trying to count the peak to peak, the time period between the two peaks, right? So you count many of them and get an average of it, so you can get a heart rate. But there will be a DC offset, and this is very common. It's very common. So like I said, if you have DC offset, the first step will be a high pass filter. It's a high pass filter with a capacitor in front of it at the very beginning, and then you have a resistor shorting to a VREF. So we'll go through this really quick. Why we need the VREF? But high pass filter is a capacitor first and then a resistor, and that's called a passive high pass filter. Passive high pass filter, and usually the performance is just okay. It works, but not the best. It doesn't have a op-amp involved, and usually we define that type of filter just the RC filter or passive filter. So that signal comes out from the receiver here and goes through the high pass filter first. So the signal was swinging around the certain DC level, and that DC will be gone after that. Only AC is left. So the question is, why do we need the DC part to be gone? Why is that? It doesn't carry information, and that DC offset could be anywhere. Let me show you. Which is bad, right? So your op-amp, in circuit 1, we did a dual power supply, but in real world, we very rarely we do that. So it's usually either it's ground and VCC, right? So that's for 2 rails. And if you have this 2 rails from 0 to VCC, and that's going to be the range of voltages to swing, right? So it's going to be in this range. So your DC offset could be here from the sensor, it could be here. If your DC offset is here, then your signal, if your signal is small, which is still fine, but the thing is, if you amplify the AC part of the signal, it could be amplified for the voltage below that DC offset like this, since you still have room to swing it. But for here, it's going to be cut. It'll be cut off on top, so you don't have the room to swing it. Okay, same thing for here. So you can, like signal like this, you can amplify. If you amplify it, we'll show you a signal like that. You are losing information at the bottom. So in that case, that's why the first step is to add a DC bias. Okay, just lift your signal to the middle of the range. So you have a signal like this, you amplify it, you have an equal swing towards both sides of the DC offset. Okay, you can leverage more space of the rail-to-rail voltage over here. So how to do that? It's called superposition. So AC signal passes through the high pass filter and the DC component will be gone. And you add a VREF. It's a reference signal. That's a DC bias. You add it to it. So this signal is added to this wire, and it's being superimposed to this point. So it's adding to your AC. So basically, you are lifting that AC to this DC level. And we're not doing calculation to it because it's just basically a superposition, right? So it's being superimposed to here. And the VREF is being provided by a Zener diode, and it's one of the questions on the in-class sheet. Okay, and so this resistor shouldn't be too big, shouldn't be too small, and the reason they chose 380 is that if it's too small, this breakdown current can be very high, and it won't be able to limit the amount of current. It will damage the Zener diode. So I'm going to show you the IV curve. Do you still remember how to draw the IV curve for the Zener diode? For diode, for example, this is I, right? This is V, and that's the V forward, like this, plus minus. It's a regular diode, right? Regular diode. So ideally, regular diode is gonna do what? Not exactly ideally, but usually this is a V. We can call it VTH, threshold voltage. It's also called V what? V B? I forgot. Probably not VB. Just the building voltage, right? So that will turn it on. Usually for silicon, it's 0.6 volts. But that's for forward bias. So whenever this voltage becomes negative, which means that the diode is being reversely biased, right? Reversely biased. If you go, the voltage goes to the negative region over here. And usually for the regular diode, it's not fabricated in the way for the Zener diode. So it usually will stay here, like there will be a little leakage of the current, and it will break down. So whenever it breaks down, you are seeing a huge current going through it without any voltage changes. So you can see the delta V here is tiny, but you are getting a lot of current. So it breaks down, and you cannot recover it for the regular diode because it's broken, right? But for Zener diode, there's a certain way to fabricate it, and it's probably heavily doped or something. I don't know. Dr. Jesse probably knows it. How to fabricate a Zener diode? What are the differences? We can also, just Google it, right? So the Zener diode is able to handle reverse breakdown and recover it. So this is, you can go back and forth as this curve for the Zener diode. So Zener diode's symbol looks like this, and we usually only use the reverse biased configuration for the Zener diode. If you need a diode perform this way, don't pick up a Zener diode. I've seen students pick up Zener diodes from the lab, just use it as a regular diode. That's ridiculous. Zener diode is for voltage references. Keep in mind, Zener diode is only used as a voltage reference because the foundries is able to mix all these dopants, whatever the materials in there, to modify your VZ, right? So this is called VZ, the breakdown voltage, and that could ranges from 0.5 volts. I'm just giving examples to like whatever 6 volts. So it changes a lot. So this one can shift at different ranges. You can purchase different breakdown voltages for the Zener diode. So for this one, you can see that this Zener diode is rated as VZ equals 2 volts. Okay, and we reversely bias it. So just to break it down, right? So whenever you have a resistor connect to VCC, it applies the voltage across it. Whenever it reaches 2 volts, it breaks down, and there will be a lot of current going through it. So whenever VCC increase, for example, if we can increase VCC, if VCC increase, this voltage almost does not increase at all. How that works? If you increase VCC, your current increase, right? And with the current increase, why is this one just doesn't increase? Yeah, it's just drawing a lot of current and dump it to the ground. So by looking at the IV curve, the voltage doesn't change. The x-axis is voltage. The voltage doesn't change. If you have a little bit more voltage, it just increases your current flow even more to cancel it. So voltage does not change. And that's being used as a reference voltage being provided to this point. Okay? And then following that, for this part of the circuit, so keep in mind, this is not a special design, okay? This is a very common design, and everyone as a computer or electrical engineer should know, okay? And it can show up on the interviews as an interview question because it's so common. And I even believe that in the future, because these designs doesn't really change too much, I think AI will directly just do everything for you. Instead of having the whole lecture to teach you guys how to design the future, I think it's just going to be a chat window. Is tell them all the cutoff frequencies, what are they, and the power supplies, and the reference voltages. They will just design the PCB for you, and probably just ask you approval, and you click that approval button, and it will send it to JLC PCB in China to fabricate it. And then someone will ship it, and a drone will deliver it to the campus, and you just grab it, and the robot will solder everything for you. Because AI could even handle even more complicated projects, and this is so established. But could still be an interview question, right? Could still be an interview question. So this only works for the ones who understand what's going on. You couldn't ask a high schooler to design this. Right? You still have to understand the circuit, so you can approve it. All right. So the next stage is something you must know, right? What is that circuit? It's a low-pass filter. It's also an amplifier. And so if you see this circuit, you need to answer these two questions, right? So first, it's a low-pass filter. Second, it's an amplifier. And they will ask you, if it's a low-pass filter, what's the cutoff frequency? If they ask you it's an amplifier, what's the DC gain? Keep in mind, DC gain, low frequency gain, because it's a filter, so the gain varies depending on the frequency of the signal. Okay? If it's a low pass filter for a high frequency signal, the gain will be smaller or higher. Why?
Because it's only passing the low.
Yeah. So low pass filter only pass low frequencies, right? So high frequency signal will be attenuated. And then you are getting a less voltage output. So which means V out over V in will be lower, which means the gain will be lower, right? So that's why I'm asking you about the DC gain. DC gain, because AC gain varies depending on the frequency, given the AC curve of the transfer function, right? So what's the DC gain? So in order to know the DC gain, you need to tell if this is a non-inverting or inverting configuration. So the signal goes to the inverting or non-inverting terminal. Nope. Inverting is a DC VREF. Yeah. So see here, AC signal being filtered, right? So that's a signal which carries information, goes to the non-inverting terminal. So the non-inverting configuration. So for non-inverting configuration, what's the gain if you have a closed loop circuit? What's the gain? 1 plus RF over R1, right? When did you take your analog? Circuit 1 is 2 years ago, but analog is when? Now?
I haven't taken analog yet.
Haven't taken analog yet? Last semester? Couple years ago. Okay, remember that this shouldn't be something that you have to think about or have to Google, right? And I'm serious about it. So for closed loop configurations of the op-amps, we use them to amplify IC signals. So you guys know that, right? For open loop, these are compators, but closed loop, these are amplifiers. Okay, so it's always negative feedback. You guys know that, right? So amplifiers using op-amps, it's always negative feedback. Always, never positive feedback. So in that case, it has to be like this. Okay, make sense? Doesn't matter how they draw it. Sometimes they draw it that way. This is probably a more common way to draw it. It's the same thing. So this is called RF, is a feedback resistor, and there will be it's called R1, it's an input resistor. I got a VI, and ground it, and you have plus minus 15 volts, for example. That's a classic circuit 1 op-amp 101 circuit in the lab, right? So it's an inverting configuration because the signal goes to the inverting terminal of the circuit. And keep in mind that this is called inverting. It's an inverting configuration. And this amplifier has another name, it's the TIA. It's called transimpedance amplifier as well, because this guy actually amplifies the current into the voltage. And this is the gain resistor. Okay? This is not amplifying voltage, this amplifies current into a voltage. So it's called transimpedance, and it converts the current into the voltage. The reason for that is because this is a virtual ground here. Okay? So the input is actually converted to a current immediately after this resistor. So it's basically VI minus 0, which is 0 volts here, over R1. So whatever being amplified is actually current. Okay? So current goes through that's a gain resistor, and because current goes through resistor will cause a voltage drop. So your VL is basically that voltage drop for this current goes through this resistor. So that's why it's actually a current to voltage converter, or it's called a transimpedance amplifier. So this guy is not amplifying voltage directly, but eventually what shows to you what the outcome is, you got a VI in the beginning, and you do have a VL. So you can also, if you write down the gain or the transfer function, is actually VO over VI equals minus RF over R1. Okay, so for this one and this circuit, you should be able to draw it and teach a high schooler without looking at a textbook. We graduate from this program. This is required. This is just so fundamental. Okay. So what's the is there a phase shift from VO to VI? Yeah, 180, right? So you got a V in like this. Your VL is going to look like this because it's being inverted. That's why it's called inverting configuration, right? Okay. For the non-inverting configuration, that's the DC gain, right? It's the gain. Why is the DC gain? It's the AC signal. Why is the DC gain? Why we call it DC gain? It's just a name. So DC gain means a low frequency gain, right? So these are all linear components. So there's no cutoff frequency. It's always going through. But this guy probably have a limited frequency in there, but usually it's something else. But this one, there's no filter in here. It's just resistors, linear components. It's just a voltage gain. We don't say DC gain here. Whenever we have a filter, we call it DC gain, right? There's no filter here. But for the non-inverting, okay. So it's always feedback like this. She's amplifying a voltage. It's a voltage to voltage amplifier. So the non-inverting configuration is not a TIA. It's just a voltage amplifier. And there's no phase shift because V out equals 1 plus RF over R1. And there's no minus sign, so there's no phase shift. VI and VL has the same phase. Can you tell from here? Is there a phase shift? No phase shift. These are just constants, right? Constants. And output will have the same phase, right? And that's the gain of it. That's the gain of it, voltage gain. So for non-inverting, you have a 1 plus. 1 plus. For inverting, there's a minus sign. But they are both 90 feedback. Keep in mind. That's the only That's something they share. It's a common thing they share. If you add a filter, if you add a capacitor here, this becomes a low pass filter, and the cutoff frequency is 1 over 2 pi RC. So if you come back to this circuit, is there any difference between this and this? Is this and this? What's the difference? Probably only this point, right? It's a VREF instead of ground. So we're adding a DC bias. You are lifting your signal because this guy goes through this point, and that's a virtual, is a negative feedback, so it's a virtual short circuit. So this will be added to this point as well. Okay. So it's lifting this VI signal and swing it around VREF. So don't ground it. That's the only difference. You don't ground it. Instead, you add a VREF. The reason for that is you don't have anything available below ground. So 0 volts is the lowest voltage. So you need to lift your signal to the middle between VCC and ground. So it's swinging in the middle of it. That's how to design this preamplifier circuit for the high pass filter and low pass filter with the amplifier with the DC gain. So what's the DC gain here?
48.
48. Is it 48? It's a 470 divided by 10, giving you 47 plus 1 will be 48. And that's the DC gain. That's the voltage gain. If your high pass, low pass filter shouldn't attenuate your desired signal too much. There might be a little bit attenuation, but the majority of the signal which carries information shouldn't be attenuated. And what's the frequency you expect from your heartbeat signal? Would you expect a 3 hertz?
Hopefully not.
That's too much. So what is considered as a very high heart rate? It's probably potentially hurting your blood vessel.
180.
180 is high, is the top, right? It's usually the ceiling. So you have 120 seconds per minute. So 180 is just a little bit over 1 hertz, right? It's not even 2 hertz. So for athletes,
It's 3 hertz.
wait,
3 times per
180.
second. It's 180 times.
Oh, that's
a minute.
right. It's a 3 hertz.
Yeah.
Yeah, because 60 seconds for
3
1
hertz.
minute. Yes, that's right. So it's 3 hertz. So it's possibly reaching 3 hertz, but that's the highest. So let's look at the cutoff frequency here. It's 0.4 hertz.
It's probably around 200, 210. Yeah,
200 to. Yes.
which is the absolute max.
It's not, yeah. So the thing is, you don't want to directly just use 180 or 200 because these filters is not perfect. So the attenuation or the AC curve, the frequency response. So remember, it's called frequency response, right? So which means it responds to a certain frequency. The x-axis is actually f, it's the frequency, and the y-axis is the V over Vi, it's the gain. Okay, so it's usually like this. So the cutoff frequency is over here. Usually, not directly at the corner, but usually 0.7, 0.71, 0.7 of the V over Vi.
The 3 dB.
Yes, 3 dB. Attenuation. And so this is usually called FC, is the cutting frequency. But the thing is, it's not directly going to 0. It has a certain certain slope over here. So it's not perfect, right? So there's no like perfect filter like that. So it's always slowly going down. So we should give a little bit room after the maximum heart rate you possibly can get. But anything higher than that, we consider as noise, because that won't be something come from a human heart. right? Unless you see your crush. What about the lower end? 3040 as an ASIC like you?
Yeah.
What about yours?
Mine's like 35.
Oh, jeez. It's crazy. I thought 50 or 60 will be super low already, but good. Okay. How do you consider it converted to, this could be 0.5, it's around 0.5, right? It's a 30. But 35 is like a 0.6 probably hertz, right? So 30, 0.5 hertz, right? So 2 seconds it beat once. Jeez. It's good. All right, so so for Elijah, you need to change the filters cut off frequency probably, otherwise you wouldn't be see anything, or you have to run a little bit in order to see some difference.
Yeah, probably.
Okay, so I'm gonna order different capacitors for you. So that's, you can see that this is probably the heart rate of the human heartbeat in here for the lower side, higher side, and the signal comes out. You can adjust a potentiometer to adjust the voltage output depending on your application. This is quite useful because, like I said, you got a VCC which is 5 volts, and it's being lifted to 2 volts. Okay, and so your signal is swinging around 2 volts, and can easily go up and exceed 3.3 volts. But that's not even the most important part. The thing is, our ADC, even though our IPGAs are taking up to 3.3 volts as a digital logic, but ADC is only taking up to 1 volt. That's a practical problem, right? How do we figure that out? It's given. ADC is a 0 to 1 volt ADC for the input dynamic range. There's no anything higher than 1 volt will damage it. Divide it.
Attenuate it.
That's one of the ways to do it, right? That works. Use a voltage divider. Sure.
Use an op amp.
Yep. So what about the power supply for the op amps? So you probably you're curious, you want to open up the data sheet of the op amps, see what's the lowest voltage you can give to these op amps. You don't want to supply 5 volts anymore, even though it's take up to probably 6.4 volts. And usually people just use 5 volts, but we want to use the lowest possible. So I was searching for 1 volt op amps, and I didn't see any. So the lowest is about 1.8 volts that I can see for the VCC. There must be 1 volt op amps, but probably it's very expensive. But 1.8 volts is a VCC this specific op amps can take as a minimum. Okay. But my question is, what about the reference voltage here? Because everything should swing around 0.5 volts eventually. Since our ADC is taking a 1 volt range, right? So that's from 1 volt to 0 volts to 1 volts as a range for the input of the ADC. So you want to lift your signal to 0.5 DC bias, and you swing your signal around 0.5. If you know your ADC is taking 0 to 1, right? So you want to use 0.5 as a DC bias. So your amplifier, your preamplifier, all the circuit here, the goal of building all these circuits is to give you a DC bias of 0.5 volts and an AC signal swing around 0.5 volts, but not exceeding 1 volt. So it's basically plus minus 0.5 volts swing. So based on this given circuit, so this circuit is being sold online, right? It's definitely not designed for our application. So the thing is, how can we change it to make it compatible with our ADC? So that's the first stage, right? So first stage, high pass filter, low pass filter with a DC gain, which is 48. So your weak, very weak analog signal is being amplified by 48 times. Okay, and you can use your potentiometer to divide it and eventually reduce it to a certain range. But you are not going to reduce. The DC reference here will be reduced as well, actually. Yeah, so you can change this one to reduce it. So both the DC and AC, right? So because it's being divided. It's being divided. And then that signal, it could be something swing around something, right? Because everything's being divided. And that will go to the second stage as a duplicate. It's the same thing with a high pass filter or low pass filter. Okay? So 2 stages has its benefit. You probably are wondering why we are not just directly use the 1 stage, and if 48 times the gain is not enough. So what about, because you have 2 stages of 48, so 48 times 48 is about, I don't know, 2,000 maybe. So 2,000 times amplification, right? So it's probably amplifying something swinging around like a couple millivolts level to a couple volts. Okay, so you can visualize it. And why not just using a 2,000 voltage gain for 1 stage and just get it done instead of using 2 stages, which takes a lot of space? Fine. It's because every time you amplify it, every op amp is not ideal. It whenever amplifies the signal, also amplifies noise. Right? So if you use a huge gain for 1 stage, your noise and signal are being amplified at the same time, so the quality of the signal will be very poor. So what you do is you amplify a reasonable amount, and then you got a clean signal with the signal but less noise, and then you filter everything again to get rid of the noises with another stage, and then you got a cleaner signal to noise ratio, right? And then you amplify it twice. Usually you can see for this signal is probably not too weak. I can imagine it's probably tens of millivolts, but some of the signal are lower than 10 millivolts, and you may need like 3 or 4 stages. You can see a lot of scientific instrument, they have their amplification circuit from especially optical signals with a lot of noises. They do have 4 or 5 op amp stages, exactly the same configuration. And sometimes they do non-inverting configurations, sometimes they do inverting configurations. And if you do inverting configurations, you have to use an even number of these stages, so it's being inverted twice and eventually has no phase shift. Okay, so these are just something to consider in your design. But at least for this project, we learned a lot of things, right? So first, we need to remove the DC bias, undesired DC bias from the sensor using a high-pass filter, and then we lift it by a desired DC bias, right? And then we go run the signal through a low-pass filter and a DC gain. With a DC gain, is active low-pass filter, so we get a signal amplified and get a high-frequency noise removed. And then we need multiple stages to increase the signal-to-noise ratio. Okay? Good stuff learned here. And after that, it is trying to isolate the following stage from the amplification stages by using a voltage follower. And this is another thing you must know. Okay? This is a voltage follower, or you can call it a buffer. A buffer or a voltage follower has a unity gain because there's no RF and R1. It's still a negative feedback because remember, closed loop configurations have to be negative feedback. But the thing is, we don't have any resistors added to it, so eventually the gain will be 1. So there's nothing different. The voltage are in phase, V out is in phase with the V in, and the voltage amplitudes will be the same. But the only thing this buffer does is to isolate the following stages from the front stages. So why do we need a buffer like that? It's not changing the voltage at all. It's not changing the phase, matching the voltage. Why do we still need a buffer a lot of times?
So that your load sees like basically an infinite impedance.
Mm-hmm. So you can see here, this point is shorted to the resistors like this, right? Okay, and because this has a super high or infinite input resistance, so it's considered as a disconnected circuit. So your following resistors will not perform as a voltage divider for these resistors, not affecting these stages. Imagine that if you directly connect the resistor here to ground, what's going to happen? And this resistor won't be 430K anymore, right? It's being affected. You got a current going through that resistor. So you have a super high input resistance. This could be considered as a disconnected circuit. So the following circuit is not affecting whatever the resistor connected to the front stages over here. So this is really practical. I have had a lot of senior design groups in the last year came to my office asking for the changes to the circuit eventually, right? So we add a buffer to it and just solved a lot of problems. And not just for senior design, but also for a lot of other projects as well. You just need a buffer. It just directly solves the problem. All right. And after that, you can see why it's added to it, because you can see that it's eventually shorted to a resistor as a current limiting resistor and the LED. And this final stage is used as a digital output stage. There's no negative feedback, which means it's being used as a what? There's no negative feedback. What is this used for? Comparator, right? It's not an amplifier anymore, it's a comparator. And it's comparing to the reference voltage on shorted to the inverting terminal. And it's a potential meter. It can change it to a certain DC level. So whenever it passes that DC level, this one will be switched on, right? So showing the DC voltage. On the others, the other case, it will swing back to ground, because all these ones has a 0 to VCC power rails. So this one will swing around 0 to 1, perform like a digital signal, like a comparator's digital signal, and that will turn on and off this guy. So which means whenever you have a, it works this way. So that's a pulse signal, for example, you are receiving. Okay, if you set up the reference voltage over here, and reference voltage, this is not a reference voltage for the DC bias, right? This is reference voltage for the comparator, because this is connecting to the inverting terminal. We call it VM. It's a V minus. And now I'm asking you guys to draw that digital output of the comparator. Would you be able to do that? Could be on the quiz. So comparator's VL equals what? VP minus VM times open loop gain. And the open loop gain is huge, right? So which means if VP is slightly larger than VM, it times a huge open loop gain will give you a huge output voltage. Huge output voltage. The thing is, you only have 5 volts available here, right? So in that case, if VP is a little bit larger than VM, we'll shoot up to 1 immediately. If VM is the other way, if VM is a little bit larger than VP, this becomes negative, a little negative number, but times the huge gain, an open loop gain, will give you a huge negative number, but you only have ground for the op-amp, so it's going to saturate at ground. So it goes to 0. So for this curve, we know VM is like this. VP is your signal, because the signal goes to the non-inverting terminal. Okay, so when VP here, VP is larger than your VM, what's going to happen? It becomes 1, right? But for all the rest, it's going to be 0. It only turns on whenever it's larger than VM. So when you pick up your VM, make sure it's larger than this signal, okay? Otherwise, it's counting twice. So what's going to happen if I label it over there instead? It's just a pulse signal. I don't know why they have to have this one. It's just the pulses. I have 2 peaks, one big peak, one smaller peak. Their heartbeat like boom, 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 probably, right? So if you have something like this, what's going to happen? Like this. Shooting to 5, right? So we're counting twice per heartbeat. So this one, because the heartbeat signal varies, I'm drawing a pretty good signal for you guys here, but it could be very small. Okay. So if we don't have your heartbeat, for example, there's a DC bias. There's a DC bias that's being lifted. This is 5 volts. Okay, if the signal looks like this, it's being lifted to the middle, and the swing has a really small swing. If we do not have the comparator circuit, what's going to happen to the LED? You still want to see the heartbeat being indicated to the LED, right? It's a very simple indicator. Why not? Whenever the heart beats, you want to see it blinks. If you do not have the comparator circuit, you only use AO, A out, analog out, like the amplified analog voltage, which looks like this. What's going to happen? If you connect this signal to the LED, what's going to happen? First, it's always on, right? Second, it's sometimes getting brighter, sometimes getting lower, right? It's not showing a on off. It's just dimmer, brighter like that, which is not ideal. So that's why we want to see the beats. So we connect the signal to a comparator in order to see that on off signal. So this is just a signal on the board. But keep in mind, we are designing an ASIC. So we are going to detect this digital output. So even though it's a digital output, but we're digitizing this guy. So we consider this as an analog output, and we're counting the frequency of it. So you have to see this rising edge, detect the rising edge, and you start a timer, and you see another rising edge. You probably do 10 of them, right? And calculate the average of the period here. So I have to use the pico blades to do the job, right? So what if we don't use ASIC, but just use a very simple digital circuit? Are we still able to find out the frequency as well using Verilog? Something we can explore in the future, but just to let you guys know that the heart rate detector is a simplified version of this project. So the next time I'm going to use the design to design a real oximeter. The oximeter will detect your the oxygen saturation ratio, which indicates how well your lung is working, it's functioning. It's become super useful during COVID or any of the what's that called, outbreaks for the diseases. And so in that case, you have to use 2 colors of LEDs. Usually, I forgot the colors, but for example, blue and red, right? and then you detect the voltage levels over here, and you calculate the ratio of the two colors to find out how much blood is being taken into your blood, the blood cells, red blood cells. That characterize the functionality of your lung and become a very important vital of your body. So in that case, if we're detecting accurate analog signals, we have to use ADCs. We cannot just directly use a pulse sensor, just measure the frequency, because the frequency is important, but it's just one of the vitals we need to capture. Okay, so there are a lot of other things you need to measure, even including the voltage levels over here compared to the peak. These all carry information. These are biomedical signals available from the healthcare and being used for doctors for diagnosis. So, but this time we just take baby steps, right? So we are not doing everything. So as long as we can digitize this DC output, this digital output, and measure the frequency using pico blades and display it through the OLED, we're good. So next year we'll let the other students who use whatever you guys design and added another ADC feature of it for real diagnosis of the vitals. Okay, and so you can see this first tutorial. So these are snapshots from the website, whoever developed this at the very beginning. So these are the signals being captured, and they used a oscilloscope. So after we soldered this board, we should be able to connect it to the oscilloscope and see the signals. So that's one of the tasks of the project. Let's take a look at the tasks. So the board will be here hopefully Thursday or Friday. So next week in the lab time, we will assemble it and work on the oscilloscope part, which is task 1 of the tutorial 1 of the project. So assemble the module and use the benchtop power supply. So this is how you can verify it using oscilloscope. Since we know our ADC is taking from 0 volts to 1 volt, okay? So before you connect it to the ADC, you have to verify the voltage level on the oscilloscope. So the reason to see that, the way to see that is you add a 0.5 volts as a reference voltage to the circuit, and we are not designing a reference voltage circuit. Instead, we use a benchtop power supply. Remember the reference voltage over here? This guy? Right? So the Zener diode is giving us 2 volts, which doesn't work for our ADC. So what we are going to do is using a power supply. You just set up 0.5 volts. Just make it simple, okay? And fit it to the VREF point. And if you look at the PCB, with a circuit like this, right? The PCB already printed the traces on the board, okay? So how could you add a VREF to this point without being affected by VCC and this Zener diode? That's my question for you guys. I just being creative, right? Modify the board a little bit. How could I directly give a 0.5 VREF from the benchtop power supply to the whole circuit, because all the VREFs are being used for the circuit as DC bias? How could we add it externally and without being affected by the VCC and the Zener diode? How could you do that? You just don't solder these 2 components. Just leave it open. So VCC cannot get to this point. Leave it open, right? Also leave this open so ground cannot get to this point. Then you find out the voltage, a metal piece, it could be a pin, could be a whatever, you solder a wire to it, and eventually connect your 0.5 volts to this point, so the 0.5 volts will be delivered to the VREF. Okay? So you can see there could be a lot of quizzes from this project, right? This could be a quiz. the low pass filter thing, the DC gains, the configurations, non-inverting, inverting could be quizzes. Fill a quiz here is way better than fill interview questions in the future. Okay? Question on this so far? Okay, let's go through all these questions. So task 1, assemble the circuit, give a 0.5 volts reference, like what I just said, and then the VCC couldn't be less than 1.8 volts. That's what I saw from the data sheet of the op-amp. So you still have to use 1.8 volts. So eventually it's going to look like what? It's going to look like what? So you have your 0 to 1.8 volts. Is this one affecting your ADC? Is this ground of this circuit? So is this ground of the circuit a common ground for the IPGA? The ground of the preamplifier of the PCB here, the ground of this guy, is the ground here is a common ground of the IPGA? You just say yes, because it's always the case, right? Common ground, what's it called common ground? It's common. It's everywhere. Why? You are outputting a 0 to 1 volts from the amplifier, and you want your IPGA treat that voltage range as 0 to 1 as well, not 5 to 6. Does that make sense? The only way to do that is they have the common base. The common base. So whenever you have a common base, here the amplifier lift it to 1 volt, and the IPGA will see it from 0 to 1 as well instead of 5 to 6 because they have the common base. Okay, that's why you need a common ground. Okay, so in that case, what about the power supply for this guy? It's 1.8 volts, right? Does it affect anything of your IPGA power supply? No, it's not a common power supply. You have common ground, but not common power supply. So the power supply for this is separate from the servo servo's power supply, right? So your IPGA is powered up by the USB port, 5 volts, and it's being regulated to servo servos. But however, the designer for the ADC decided to use 1 volt as a range for the ADC, which is fine. I mean, it's very common. It's usually the smaller technologies. I believe the Basis 3, the Arctic 7 series chip is using 28 nanometers technology. So it's 28 nanometers per transistor length. So it's a really small technology, but very modern. So that's why you can run at 100 megahertz, way faster than your Arduinos, right? Arduinos are usually 350 nanometers, like 40-year-old technology, able to handle 5 volts. But the core of your IPGA, even though you have servo servos for the pads, it's for the chip. But the thing is, it's being lowered to 1 volt for the CPU. It's a technology for the modern ASIC. Just to let you guys know. You know, for the modern cores, even for 180, I think we do the same thing. Let alone the lower voltage, lower technologies. So servo servos could be a power supply of the chip, but the thing is, whenever the voltage is being delivered to the core, the CPU is running at 1 volt. Okay, that's very common for the modern technologies, especially for the 28. You know, for lower, probably 1 volt as well. So the thing is, why 3-point servos still needed? Why 3-point servos is still needed? I mean, since our core, the CPU and everything, all the logic is running at 1 volt, why do we still need 3-point servos to be used? It's a really common power supply, right? And it's giving you a good range. Sometimes your analog signal is swinging around 0 to 1, 0 to 1.5, and you don't want to directly just use 1 volt, which give you a very little space for other things. So your power supply is 3.3 volts, power up the chip. But the thing is, the chip has cores, but also has pads. We didn't show the pad circuit. The pads have the ESC diodes, have a lot of buffers and digital circuits, and these pads, these digital circuits next to the pads of the IC chip, they use 3.3 volts as a power supply. That's very, very common. So 3.3 volts for these pads circuits. But whenever the pads output that 3.3 volts to the chip, and there will be voltage regulators, and the name of these circuits are usually called regulators. It's not low dropout voltage regulators. They could drop out like 1.5 volts easily. So that is why when you are doing 3.3 volts and you are regulating from 5 volts, which is still fine with the cheap regulators, but if you're using one cell LiPo battery from 3.7 volts per cell to 3.3 volts, and in that case only 400 millivolts loss is allowed, then you have to use the low dropout voltage or low voltage dropout regulators. These are special ICs, are more expensive, but higher quality, right? So there will be voltage regulators for that purpose. So for our application, IPGAs are using 3.3 volts, right? ADCs are using 1 volt, and your op amps are using 1.8 volts, which doesn't matter because your signal will swing because that's the op amps range. But the thing is, you only lift it to about a third of the range, and you are only swinging it plus minus 0.5 volts, so up to 1 volt. So you are not using this space, which is fine. Who cares? Because the ADC is not taking any voltages in this range. But your op amp can power it up to this range. And it's actually not taking anything less than 1.8 volts. You can try it. It doesn't really matter. Can we use like higher voltage here? Does it help or does it hurt anything? Use a higher voltage here. It doesn't hurt anything, right? Because we always lift it to 0.5. Our VRAF is 0.5. And we always swing it within that range. So how do we control that swing amplitude? How do we control that? How? How do we make sure it's within this range, 0 to 1? It's not exceeding this, which damages the ADC of the IPGA. How?
That's what the potentiometer.
The potentiometer of the voltage gain of the voltage amplifier, right? So you got 2 stages of these ones, and if you see, hey, this is still too much because this commercial board, the Easy PAL sensor, is not designed for 1 volt, and the gain is just too much. Instead of amplifying it to a certain level and then divide it, why not just replace the resistors? You could reduce the DC gain here if you want. Okay? So there are a lot of things to change. Change the DC gain or twist the knob here, right? Okay. So the first goal is to show a voltage DC output from 0 to 1 volt, DC output from your sensor after adjusting the DC gains and the potentiometer, and display it on the oscilloscope. It has to be 0 to 1. It has to be 0 to 1. Wait, so would that be possible? Because your comparator is powered up by 1.8 volts. It's going to be from 0 to 1.8. Right? It's going to be 0 to 1.8. What could you do? Huh? Voltage divider again? Yeah, I think so. Let's do it. Let's do a voltage divider again over here. Yeah, the analog signals here, you can control it to swing it around, to swing it from 0 to 1, but does that matter? I think we should, because it's for next year's, right? So we should always keep it within 1 to 0, 0 to 1. But for here, because this guy is powered up by 1.8, which is the minimum voltage power supply for the power supply, so the digital signal will be 0 to 1.8, and then you have to divide it further. Okay, so make sure that you show an analog signal output 0 to 1 swing, and also digital signal from 0 to 1 swing as well. Okay. Task 2. Design a simple voltage divider to reduce DO to 1.1. Yeah, so this is task 2 is for the digital output, so you have to divide it to 1.0 to 1 volt. Okay, so 20 points for the first one, 10 points for the second one, and use a oscilloscope to record the resting heart rate, and then briefly run a jump to raise your heart rate, and take another measurement to confirm that the device actually detects both values. Okay, so if you just show one resting heart rate, we don't know if that works, right? If you increase your heart rate and then you'll see a faster frequency from the oscilloscope, we know it works. It's just verify the functionality of the circuit further. So make sure that the signal you are getting is not a noise; it's actually a heartbeat. So that's for this task, the 3 tasks for this tutorial, and you can see it worth probably 50 points. And let's go back to the syllabus, see how much the percentage of the course project. So keep in mind, we don't have finals. So this one will be the last big project or assignment for this class, and that takes 20% of the course grade. Do you prefer a final exam? So you prefer a project?
Yes.
Okay. Prefer both? No. Too much. It's just only do project. I think it's good. So that's why we have 3 different components of the project. So the first one I think is really doable. You get a board, you solder it, test it, got a heart rate, got 50 points. That's considered as part of the course project. And then we have the XADC. Okay, we'll cover more about the ADC on Thursday. So the ADC has certain structures, and there's example code online. It's pretty simple. I think we could easily show convert the analog signal into a digital output to the LEDs really quick. Just see a pattern depending on the analog input. So the example code is provided. I think it's click and download it. It's over here. Okay, so this is not a problem. We'll talk about the details of all of it on Thursday. And then we have a course project with some tasks over here. So how do we do that? All right. So your amplifier, the Easy Pulse sensor module, output a digital or analog signal from 0 to 1 volt. And we are using the digital signal, I guess, instead of analog one. But the analog one, it's hard to detect the peak. You should be able to. Remember how did we do that with the C in microcontrollers? Let's write a lot of code, right? And we convert it to assembly will be too much. But if you are able to do it, it's comparing 3 values, right? So the previous value is smaller than the current value, and the next one is also smaller than the current one. Then we know that it's a peak. Then we record the time, but we have to use the interrupts and all the timers. Is getting very complicated. I don't think we are able to get it done with assembly easily. So that's why the alternative here is converted to digital signal, so we can only detect the rising edge, right? So we're probing the output. If we see a 1 or a rising edge, we record it. It's probably easier. Okay. So that one is being sent to our XADC. You digitize it, even though there's different ways of detecting it, because it could be you can totally bypass your XADC, but only look at your the rising edge, right? You can just probe it. It's 0 or 1. If it's a 1, then you record it. So, but we should use the XADC because it's just for the next step, right? For the next year, we will have to probe the analog signal. So we still have to digitize it, and then use the pico blades to do the frequency measurement, and then send it to the SPI leader transmitter module within your IPGA, and then it sends out to the OLED display. And the OLED display has a couple of things we need to talk about on Thursday, with the timing and everything. So that need to be handled by your Verilog. Okay, with the 3 tasks over there. All right, and there's no lab today. Just focus on the assignments for this week, and next Monday, another due on Monday. And we'll see you guys on Thursday.